piece we are talking about are two theorems. In this section, we're going to look at the mean value theorem and what's called Rolle's theorem, and how to apply those things. So the first one we're going to start with is Rolle's theorem. It says, let f be a function that satisfies the following three hypotheses. So first thing, on any problem that we use Rolle's theorem, you have to make sure that it is actually a problem where you can use Rolle's theorem. So the first thing, you are going to have to know these hypotheses. You have to know when this actually works. So in order for Rolle's theorem to work, first, it has to be continuous on the closed interval, a to b. So no breaks in the graph. Remember, things that make it discontinuous would be like vertical asymptotes. If the denominator is 0. If you're talking about radicals, square root, fourth root, you can't have a negative under there. So we're looking at pretty basic things that would make it not continuous. Piecewise functions, you have to make sure the pieces match up. Second piece, it's differentiable on the open interval. So it's okay if the derivative isn't defined at the endpoints, but it has to be defined everywhere else. The third case is the two endpoints have to be equal. Okay? So it's saying if you have a function that is continuous from the closed interval a to b, so between two x values, there are no breaks in my graph. When I plug in those y or those x's, they have the exact same y value. So if I am going to draw any kind of continuous curve that hits those two endpoints, it's saying then there is at least one number where the derivative will be 0. How many times would this derivative be 0? 2. So if you're going to start and end the same spot, the only way to do that is at some point having a maximum or a minimum. Unless you just had a horizontal line. And if your line's horizontal, what's the derivative everywhere? 0. Alright, so the next slide I just had some of those pictures like I just drew there. If it's a horizontal line, it's always 0. You could have a single max, you could have the one like I did where it had both, you could have a single min. It doesn't tell you how many there will be, but there's at least one. So, let's look at an example. If the position of a moving object at two different times is equal, what does Rolle's theorem tell us? Okay, so you're taking an object and your position at two different times is equal. So it might be, a car that's driving, starts and ends at the same spot. It might be, I throw a ball, it starts and ends at the same spot. If that position is equal, what's going to happen somewhere? Isn't it? Go back and read Rolle's theorem again. What's the conclusion? If those conditions are met, what has to be true? The derivative equals 0. If I'm talking about position, what's the derivative of position? Velocity. So if the position is equal, saying somewhere the velocity is 0. If I'm going to take something and throw it up in the air, it will come back down and hit where it started, so its position is equal. But at some point it had to switch from a positive velocity to a negative velocity. So at some point in there the velocity had to be 0. So that's all this is telling us. Anybody else, Joan? example where we're actually going to have to do everything. So suppose f of x equals x to the 1/2 minus x to the 3/2 on the closed interval 0 to 1. Find a number c that satisfies the conclusion of Rolle's theorem. Okay, first we have to make sure we can use Rolle's theorem. So keep in mind, what does a 1/2 power mean? You know, this is just saying a square root of x minus a square root of x cubed. What kind of numbers can you take the square root of? Well, as long as they're positive, we can get an answer, right? If I'm talking about 0 to 1, then would this be defined everywhere? So it's continuous. So you don't have to provide me a lot of justification, but you do have to recognize that. So the first condition, f of x is continuous on the interval 0 to 1. Okay, second thing, it has to be differentiable on the open interval. Okay, if you think about taking the derivative of an x to the 1/2, you get 1/2 x to the negative 1/2 minus 3/2 x to the 1/2. If you have a negative, that just puts it on the bottom. So what number will not work in this derivative? 0. 1/2 x to the negative 1/2, that's the same thing as saying 1 over 2 square root of x, right? So as long as x isn't 0, we're okay. Now the rule is it has to be differentiable on the open interval. So we're okay. It's not defined at 0, but it is defined everywhere on the open interval. Okay, that right there is 2 points on a test or quiz. So if you are not telling me those pieces, you are going to lose a lot of points. What's the third condition for Rolle's theorem? F of A equals F of B. So we have to plug in a 0 and a 1. We're going to plug in our endpoints to this equation. If you put in 0, square root of 0 minus the square root of 0 cubed, what do you get? 0. If you put in a 1, square root of 1 is 1 minus the square root of 1 cubed. So 1 minus 1 cubed is 0. That's your third condition. If those three conditions are met, then what does Rolle's theorem tell us? There is a point where the derivative is 0. So we have to set our derivative equal to 0. The derivative is 1/2 x to the negative 1/2 minus 3/2 x to the positive 1/2. If you're trying to figure out what makes that equal 0, I would recommend rewriting it a little bit. We have two options. We could factor out a greatest common factor here, or we could rewrite this using like radicals and fractions. What do you guys prefer? Okay. What if I factor out a 1/2 and a 3/2? If I take out a 1/2, you take out the smallest power of x, so that's a negative 1/2. So if I take that out, that's a 1 minus, this would be 3. When you factor it out, you subtract exponents. What's 1/2 minus negative 1/2? It's 1/2 minus negative would make plus 1/2, which is 1. Okay. So it's just basically saying 1 over. If you prefer to write it like this, you can. What's going to make that equal 0? Well, 1 over 2 radical x equals 0? No. What would make 1 minus 3x equal 0? One-third. Is 1/3 in the interval 0 to 1? Yes. So we found our point that made the derivative 0. Okay. I want you guys to take a look at the next example. Take a couple minutes and see if this meets the 3 requirements for Rolle's theorem. Goodies? Let's think about what this means so we can decide if it's continuous. A 2/3 power is like saying the cube root of something squared. So if you think about what you know about a cube root graph, that's just like your basic cube root is just like a sideways chair. So is that defined? Yes. If we think about our cube root, it doesn't have any breaks in it. You can do the cube roots of positives and negatives. So it is continuous. That part is okay. All right, second piece, we need to know if it's differentiable, if the derivative works. So let's find this derivative. Derivative of 1 is 0. Bring down your power. That is a negative 1/3. So let's think about what that means. A negative puts it on the bottom. And it's a 1/3, so it's like saying the cube root. So it's negative 2 over 3 times the cube root of x. Is there any problem with that? Is there anywhere that's not defined? Yeah, this is undefined at x equals 0, because you would get 0 on the bottom of the fraction. Now, if 0 isn't in our interval, we don't have anything to worry about. But is 0 in this interval? Okay, I'm going from negative 1 to positive 1. So that is in the interval. So I can say f prime of x does not exist at x equals 0, which is in the interval. So we can't use Rolle's theorem. Now, if my interval were from 1 to 2, would I have been okay? Yes. In that case, we could have used it because it's defined everywhere in that interval. Okay. Let's look at some more. Let's decide if we can use Rolle's theorem for this one. What kind of function is this? It's a polynomial. If you remember back at the beginning of the year when we talked about being continuous and differentiable, polynomials are always continuous and they are always differentiable. So if it is a polynomial, you can tell me right away f of x is a polynomial. So it is continuous and differentiable. And you don't really have to provide any justification for that other than telling me you recognize that it's a polynomial. Okay, what's the third requirement? So let's plug in our endpoints and see if they give us the same thing. So if I put in a -2, -2 to the third is -8, minus -2 squared is 4, minus 4 times -2 is 8, minus 2, and I get -6. If I put in a 2 to the third is 8, minus 4, minus 8, minus 2, and we get -6. So my endpoints are equal. That's the third requirement. Okay, since those three requirements are true, we can do Rolle's theorem. To do that, what do we have to do? Derivative. We need to find out where the derivative is 0. So the quadratic, it's not a 1x squared, so we can do shortcut. We could try box method. Is there anything that multiplies -12 and adds -2? No. So if box method doesn't work, what do we do? Quadratic formula. So opposite of b, +2, plus and minus the square root of b squared minus 4ac all over 2a. So that gives me 4 plus 48 square root of 52. Since I'm trying not to use a calculator, let's just keep working with this. I need a perfect square that goes into 52. That would be 4 and 13. So I get 1 plus and minus radical 13 over 3. Now, I got two places where the derivative is 0. You do need to confirm that they are both in your interval. We were going from -2 to +2, so we're going to be okay here. If I were going like from 0 to 2, then I would have to throw out the -1 of these answers. So you will sometimes get more points than we are looking for our interval. So you have to make sure for your final answer you only give me the ones that are a part of the interval. Questions on that? The next piece we're going to look at is the mean value theorem. And it is very similar to Rolle's, but a little more general. So Rolle's theorem works if the endpoints are the same. What the mean value theorem tells us is that the first two conditions are the same. It has to be continuous on the closed interval. It has to be differentiable on the open. If that is true, then we have this expression, which looks kind of complicated, but it's really not. It's saying that somewhere the derivative will equal, you guys know what this represents? In our Rolle's theorems, they were. This is like y2 minus y1 over x2 minus x1. This is the slope. So what this one says is that somewhere it'll equal the slope between the endpoints. Now, Rolle's theorem is kind of a general case of that. If you think about with Rolle's theorem, if your endpoints were the same, what's the slope between those? 0. And we were saying that the derivative was 0. Now we're extending it. Our endpoints don't have to be the same. But if I took the slope between those two endpoints, saying somewhere there is a point where the tangent line would have the exact same slope. So somewhere the derivative will equal that number. I have a couple of pictures on the next slide, just kind of visualizing what we talked about right there. So if you just take your endpoints, you should be able to find at least one. In the second case, there are a couple places where the derivative will equal the slope between those endpoints. Okay. So I tried to steal some graphs, and I apologize. Those did not. Can you see them better on your handouts than you can up here? For whatever reason, this is really hard to see up here. So we have this parabola. I'm asking you to estimate the x values that would make the mean value theorem true. And this one is on the interval 2 to 4. So if we start when x is 2, that's right here. And then when x is 4, that's right here. I'm going to give you guys a ruler.